This is Chapter 9, Part 2. We're going to talk about confidence intervals in this lecture. So first thing we're going to start off with are some definitions. And we're going to say the sample proportion p hat is a point estimate for the true population proportion p. And if you think back, the very first time I described this idea, I made the analogy of trying to capture a fly using one of two things: BB gun or a fly swatter. And I think it's easy to make an argument that using the fly swatter is going to have a higher confidence than the BB, because the BB is like a point, the fly swatter has area, so the chance of hitting the fly with the fly swatter is much higher than with the BB. In the same sense, when we take our point estimator, in this case p hat, that's the BB, and then we add and subtract a few standard deviations or standard errors, and what we create instead of a point estimate or a single point, what we do is we create an interval of possible values, thereby increasing the confidence. Now there are going to be some specific formulas we do to establish the actual level of confidence, but this is the basic idea. So a confidence interval estimate for the population proportion is an interval of values. It's a set. It's an interval which is a set of values rather than a single value. And we can be quite confident that it contains the actual true population proportion. The other important definition to understand is the confidence level. And this is the probability that the estimation method will give an interval that contains the parameter that we're trying to estimate. Now, we denote the confidence level using 1 minus alpha. And alpha is the same alpha. It's if we were talking about hypothesis testing here, it'd be the type 1 error rate. And in this context, it still is the type 1 error rate, because we could use the confidence interval in terms of a hypothesis test. But when we take 1 minus alpha, that actually gives our levels of confidence for the particular confidence interval we're talking about. Now, the deal is this, okay? It's a common misinterpretation. Okay, and that's that, for example, if the level of confidence is, say, 95%, a common misinterpretation is to say that there's a 95% probability that the true parameter is in the interval. And the reason this is wrong is because when we make this interval, when you think about the number line, okay, which is going to be the set of all possible p hat values in this particular case, when we establish an open interval on that for that set, what ends up happening is that p, the true parameter, is either in the interval, probability is 1, or it's not in the interval, and then the probability is 0. So the probability of whether or not the parameter is in the interval is 1 or 0. 95% is an actual, what I like to think of as a capture rate. So the way I like to think about the confidence level is it's the capture rate. So if you think about the goal being capturing the parameter, then 95% is the frequency with which we successfully capture the parameter. And again, one of the questions on your final exam is to give the confidence level as a frequentist interpretation, and that is the interpretation. Frequentist comes from frequency, and the frequentist interpretation of probability is in terms of the frequency with which the event happens, if we're talking in the most general case. And in this example, it's the frequency with which the interval captures the true parameter when we use the particular estimation method. Basic idea for the structure is we take our point estimator, p hat in this case, we add and subtract a few, certain number of standard errors of the particular point estimator, and that plus or minus is what creates the boundaries of the interval. So another way to picture the situation is to recognize that we're modeling, again, we're modeling p hat. We're assuming that there's some true proportion out there. And so when you look at the axis, it's labeled with p hat because that's the variable. P is perhaps unknown, and it certainly is if we're trying to estimate it, but we're assuming there is such a p. That's going to be the basis for this normal distribution that we're going to use for our estimate. So if we go to adjusted standard deviations, or this will eventually be standard error, but right now we know those parameter values that we're assuming. And so if I take the p, the parameter value, add 2 standard deviations on either side, then by the empirical rule, because again, this is a normal, we're assuming that p has a normal, or p hat has a normal distribution, then if we go about 2 standard deviations, then we have 95% of the possible domain values covered by the normal distribution, and that's where the 95% confidence comes from. The actual p hat value, as being indicated below, is not going to equal p. We don't expect that. But what's going to happen is we get some p hat value, and notice when we grow out the boundary values to create the interval, if we based it on 2 standard deviations, then 95% of the time that parameter value will be on the interval. Now on a particular interval, we're not going to know whether that parameter value is in there or not, but what we will know is that when we use the process, 95% of the time we capture the parameter. So one of the issues here that we have, though, is that since we're estimating p, we really can't use it in a formula. It's sort of the same situation that we had when we were modeling the sample mean, because if we knew sigma, then we could use the z distribution, and we could use the actual adjusted standard deviation. But here we have we have to use p hat because p hat's the estimator. And so again, we have that same terminology, standard error. So sometimes we use the term standard error for the actual standard deviation, and the estimated value is called the estimated standard error. But the convention is to use the term standard error only when the standard deviation of a statistic is estimated from the data. So again, one of the problematic things, or I don't know if it's problematic, but in a way it's kind of interesting, but in statistics the terminology is not well established. I guess it's well established, but there's some variability, or there are some phrases that are interchanged and not used consistently from one statistician to the next. And this is one of those cases. So the standard error could mean that that we're using the true proportion, or it could mean we're using the actual estimated proportion. But the standard deviation for that uses the p hat values is always called the standard error. And I think that's more of a convention, really. And what ends up happening now, since we don't know the true proportion and we're estimating it, our actual formula for the confidence interval involves only p hat values. Now, the z star value we've talked about before in a different context. Z star is the appropriate percentile of the standard normal distribution. And so the idea here is that, again, when we're asking the question, how many standard deviations, what we need to do is figure out, under the z distribution, how many standard deviations do we need to go to have exactly 95% of the domain covered by the function. And the answer is, again, it's the z star value that we're talking about is the appropriate percentile. Since there's 2% here, 2.5% now to be shared among these two tails, 95% area in between makes z star the 97.5th percentile. So if we were going to use the calculator to calculate this, what we would do to find z star is we would use inverse norm, because again, inverse norm finds the percentiles, and it would be 0.975, and the default is 0.1. And if I remember right, this ends up being about 1.96 approximately, which is really close to 2, which is, again, what the empirical rule would say. So here's the same sample size requirement. So again, this only works if the sample is sufficiently large. Again, since we don't know p and we're not hypothesizing p, we'll just do check the sample size based on p hat, the estimated sample proportion. So a couple other terms here. Now, margin of error. Okay, the margin of error is half the interval's width. The margin of error is what you add and subtract. So sometimes we can think of the confidence interval as being the point estimate plus or minus the margin of error. So the quantity that we're adding and subtracting from the point estimate is what we call the margin of error. For the case of a confidence interval for the proportion, the margin of error is given by the percentile times the standard error. All right, let's do an example. Back to ESP. So when we did the experiment that was designed to test whether a subject had ESP, we had a total of 96 cards. They were drawn one by one with a replacement from a well-shuffled ordinary deck of cards. Subjects asked to guess which suit of each card is drawn. 4 possible choices. P is the proportion of correct responses if the subject has ESP. The subject gets 35 correct out of 96. So what's the p hat value? Well, the p hat value, the sample proportion value, is 35 out of 96. And that's about 36.5%, or about 0.365. So the 95% confidence interval is going to be 0.365 plus or minus z star for 95%, which is about 1.96, times our standard error. So I'm going to use my calculator to calculate what the boundary values are for the interval. And the interval, excuse me, and the interval that we get is about 0.269 on the low end. That's the lower boundary. And I'll calculate the upper boundary here. End up with about 0.461 roughly. So the question is, does our confidence interval contain 0.25? The answer is no. So what does this imply It implies that the interval is giving us evidence that the true proportion, or this particular subject's true success rate, is above 25%. So since 0.25 is not in the interval, we can infer that H1 is most likely the truth. Again, in the case of the ESP problem, that assumption was that the subject had ESP. So what we're going to do, the other thing I want to show you is how you can actually calculate this easily on the calculator. So if we go to Stat and we go over to Tests and we scroll down, what we'll find is 1 proportion Z interval. And what we need to do is input the particular values. So we had 35 successes out of 96 attempts, 95% confidence level. And what the calculator gives back is the actual confidence interval estimate for the problem. Here's another example. We've got a 99% confidence interval for the true proportion. Here's the value. And the question is, what is the value of the sample proportion? Well, the thing to keep in mind here is that p hat, the whole interval, is based on p hat. In fact, p hat is the center or midpoint of this interval. So I can calculate p hat based on the interval by finding its midpoint. And hopefully you remember, once you see it again, you will remember this formula for algebra, for calculating the midpoint of an interval. And our p hat value here would have been 0.345. I can calculate the margin of error by taking this p hat value and subtracting it from the upper endpoint here. So the margin of error in this example is going to equal 0.42 minus 0.345, which is about 0.075, or it is 0.075. So that would have been the margin of error. Again, the check on this would be to take 0.345 and subtract 0.075. When I get that, I get the 0.27 back, and then add 0.75 to 0.345, and I should get 0.42, and that shows me that that I have the correct margin of error. Now, how can we reduce the margin of error? Well, there's two ways we can do this. The first way is to increase the sample size. So if we increase in, since the formula for the confidence interval the margin of error has the sample size in the denominator, as this denominator increases, the margin of error is going to decrease. So, and that makes sense. If you have a larger sample, then you should say you know more about the parameter you're trying to estimate in the population. So intuitively, that should make sense as well. Second way to reduce the margin of error is to reduce the level of confidence. And the reason for this is because, remember, the level of confidence is defined by how much area we're looking at under that normal curve. So if I reduce the area from, say, 95 to 90 or even 80, then those boundary values for Z star are going to move in. So the two ways we can reduce the margin of error is either increase the sample size, probably the best choice, or we can reduce the level of confidence. All right, here's another example. So we have a new method for detecting a type of cancer. And what we know is that among 80 adults, the method detected cancer in 5 of the adults. What we're looking for is a 92% confidence interval. Now, there's a couple of different ways to do this. we could start off by, of course, by calculating p hat. It's 5 divided by 80. Which, if I'm not mistaken, what is that? That's 1, yeah, that's right, 1/16. And 1/16 is about 0.0625. So that's about 0.0625. So that would be the point estimate. So if I'm going to use the formula, I take p hat 0.0625 plus or minus our z star value. And this is going to be for 92% area now. And then we're going to multiply that by 0.0625 times 0.9375 divided by the sample size, which is 80. So we need to figure out what the z star value is. And again, the way I would do this longhand is using the z distribution. What I need to do is to find the z star value corresponding to, well, we know we got 92% in between z star and negative z star. So that leaves 4% in each tail. So the z star value that we're looking for is the 96th percentile. So to calculate the z star value, what I would do is use inverse norm, 0.96, and again it's standard normal. But a quicker way to do it, to calculate this interval, is by just simply going to 1 proportion z interval on the calculator. So all of these formulas are built in for our convenience. So I go to 1 proportion z interval. And the x value in this case is 5. The n value here is 80. Confidence level we're going to use is 92. And we go down here to calculate, and here's the interval. So we're looking at about 1.5% to about 11%. And so we'd say this is a 92% confidence interval for P. And the important thing to understand is that there is the frequentist interpretation here. And we can think about it in a couple of different ways. One, capture rate. Oops, let me spell it right. It's capture rate. 92% of the time, this type of confidence interval will capture the true parameter. And then the second thing that we say is sometimes is that it's something like we are 95% or 92% confident. So in a sense, this is where the level of confidence comes in. And you can almost think about the confidence level as being like on a scale. So 0 is no confidence, 1 is total confidence, because a probability of 1 or a relative frequency of 1 means you always capture a parameter. So the confidence level is kind of like on a scale between these two things. So when we're down here in the 90 to 99% range, then we have very high confidence. So this is another way to think about it. It's just kind of like a relative scale of how certain you are that you've successfully captured the parameter. Now, the last thing we got to talk about here is sample size. And I don't spend a whole lot of time on this in beginning stats classes. I think it's something important to think about. But sometimes we're interested as statisticians in figuring out how big our sample needs to be to accomplish what we're trying to accomplish. So for example, in the context of a confidence interval estimation, we've got a couple of different things that we can play around with. We can adjust the margin of error, right? We can make the interval narrower, which is going to lower the confidence. We can, and then again, the other thing that we have going on here is the true parameter value, or the true proportion. Now, typically we use 1/2 for p, and then we have 1 minus 1/2, or 1/2 squared, and that gives us the worst case scenario here. That when we use 1/2 for our estimated value, that makes this quantity as large as it can be, because when you look at 1/4 times like 3/4, for example, so that's like if p were 1/4, and then 1 minus p would be 3/4. This quantity is going to be less than 1/2 squared. And of course, any quantity, any proportion less than 1/2 is going to give a value less than 1/2 squared. And so by using 1/2 squared, we're really maximizing the necessary sample size. So in any case, to figure out what sample size you need to meet the particular margin of error you're interested in at the particular level of confidence, you just simply plug those values into this formula, and then this will give you the correct sample size. Okay, well, that's the end of Chapter 9, Part 2, and this is the final lecture for Chapter 9.